McGrath, who is a graduate student here at Stanford in HCI, who has been working with Bjoern Hartmann at UC Berkeley on the Internet of Things and HCI and programming. How can we program these large, complex, distributed systems that touch the physical world? And so, without further ado.
Great, thank you, Phil. And here we go. So, hi, I'm Will, and I'm here to present the platform we've been working on for the last year and a half to try and make it easier to prototype Internet of Things and applications built on them. So we got started on this project thinking about how much effort and how much you have to write from scratch in order to make something like a Fitbit fitness tracker. In order to create one, you need to have the device, you need to write firmware for it, but in order to get that data to touch the internet where a user can view it, you have to actually have some way for it to communicate with the internet instead of just a short-range, low-power radio like Bluetooth. So most of the time you write a gateway application. So the user's phone connects to the device but also connects to the internet. But then you also need to write a server and a web app and manage all of that, and it's a whole bunch of different languages, and we feel more trouble than you need to go through. So kind of a system diagram of what that looks like. You have the wearable that communicates with an app on the phone and some server that the application creator manages, and then the user actually accesses the data through their internet browser from a larger computer or even from their mobile device. And we've looked at a bunch of apps, and many had this kind of structure that we call embedded gateway cloud. So there's an embedded device, a low-power device with a short-range, low-power radio, and some kind of sensing and often like a fairly minimal user interface. A gateway device that mainly acts as a bridge translating from the short-range radio to the broad internet, and then a cloud aspect that actually stores data over long term and lets you process the data or run more complex applications. However, as I kind of alluded to, the problems with this sort of structure are that you wind up writing code in a whole bunch of languages, and it requires fairly varied expertise or a bunch of engineers to actually get it all implemented. And there's a few problems with writing the code, including like network asynchronicity and making sure everything actually works properly. And that all kind of leads it into making it pretty hard to prototype new applications or iterate based on your existing ideas, because every time you want to change something, you're touching different parts of the stack in different languages that can cause sort of complex problems if you mess something up. So with fabryq, our goal was to try and do part of this work for you as an application or new device developer. Since most of these require some way of getting from the device to the internet and some sort of presence on the internet, we figured we could build a system that provides those two blocks for you so that all a developer has to worry about is creating their device and writing an application based on the data from their device or devices. And the protocol the wireless technology that we chose to support in this is Bluetooth Low Energy, since it's become pretty ubiquitous in smartphones currently. And the devices built on top of it are starting to take off right now. They talked a little bit about, there was actually a pretty good introduction to Bluetooth Low Energy last week. So a sort of abbreviated version is it's low power, very low power, and short range on the order of, say, 30 feet practically. But most modern smartphones now support it. All the iPhones after the 4S and all the most recent Android phones have Bluetooth Low Energy radios in them. And right now, the main devices that are commercially available that support BLE are fitness trackers and kind of prototyping maker type devices. But there are many sort of Kickstarter level things that are starting to take off that implement it. As for how Bluetooth Low Energy works, the most important things that sort of we care about from this project is that a device makes variables available in this table called a GAT table in a standard way that's interoperable between anything that supports Bluetooth Low Energy. And these variables are organized in services and characteristics by their kind of purpose and function. And you have 3 commands to read and write, where you can read the data, you can write the data, or you can be registered to be notified whenever the data changes, so you don't have to poll it to find out when something's changed. And additionally, it has a kind of star network topology in that each peripheral device can only connect to one central device, but a central device like a phone can connect to many peripherals. So our kind of vision with app development on fabryq is to create this kind of infrastructure that keeps track of what applications need what devices so that everything stays organized and the system knows as which device a user is using for a particular application as to support different gateways and different geographic locations and more complex applications. So you get started by registering any Bluetooth Low Energy devices you have. You just click on the app and say Add Device. And after that, fabryq remembers all of its services and characteristics and creates a type of device, a named type of device based on that. And then when you're creating an application, you say which of your devices that it requires, and from that it creates a kind of meta specification that tells you if you make an additional instance or installation of this app, you need to give it those kinds of devices for it to function. So those steps are basically A and B, and after you do that, we have a built-in editor to our website where you can write. It gives you a boilerplate code to start with, but then you can write more code on top of it, and it's automatically hosted, and with a click you can open it then either on your phone, on your gateway device, or on the fabryq website. So for the rest of the talk, I'll be referring back sometimes to sort of this example application example structure where a user has a off-the-shelf heart rate monitor device as well as a smart cup device that they've created that allows you to track how much liquid someone's been drinking. And in this, the user is trying to develop a medical application that helps the user track how much water they've drunk and how their heart rate is variable over the course of the day and if they interrelate. And the goal of fabryq really with providing the server and the iOS app for a developer is to make it as easy to talk from a web application written in JavaScript directly to the device as if there were no intervening layers. So from that structure to something like this. Code-wise, you write it as if they are directly available to you. And for the rest of the talk, I'll kind of be going through each segment of the system and talking about kind of the decisions we made and some of the challenges we encountered in constructing it. But first, I'll kind of go through the flow by which a fabryq command gets executed. So if, as a developer, you want to, say, get the heart rate from a heart rate device from your web application, you first launch that command in the web browser through the API. It goes up to the server and is stored on the server. Then periodically, the gateway devices that the user would have are polling the server and then pull the command down to them. Then as soon as they see a Bluetooth device that they could use to execute it, they execute it onto the device, get the result back, send the result to the server, and then usually if the network is good in both the client and endpoint, within a second you have your data on the client application again as a JavaScript callback function. So now to kind of delve into how the different aspects of the system work, I'll start with the gateway. And in general, gateways in these kinds of systems allow kind of translate between one protocol to another. So in this case, a translating between Bluetooth Low Energy for low power connected devices and making them available over the broad internet. And currently we have implemented a Mac OS X gateway and a iOS gateway application, which just run as a normal application on that device and then use the Bluetooth radio to communicate and find the devices required by these applications. One thing that we've pushed on some for this project is that not only can a gateway just be a router for commands between the client application and the devices, but since it also has a UI and a touchscreen, you can actually add some functionality in that, allowing a user to manage the devices they have, or even display custom user interfaces sent by the developer in their application. Some of the problems we hit in creating the gateway application are that, at least for iOS, we originally chose iOS because when we started, which was a year and a half ago, Bluetooth on Android, their stack was still coming together for Bluetooth Low Energy, and the iOS one seemed more robust and fleshed out. But later on, we hit some issues with iOS backgrounding. In order to conserve battery life, Apple places stringent requirements on what you can do in the background in your application when the user is not actively using your app. Additionally, iOS as a security feature makes it so that every Bluetooth device has a unique MAC address, but when you connect to it or discover them in iOS, Apple doesn't actually provide you that MAC address. It kind of obfuscates it and gives you an ID that's unique to both your device and that instance of that application, which makes things a little more confusing, because if you have one device that the user owns and they have two phones, then all of a sudden that device has a different ID on the two phones. So we store that and account for that, but it was kind of annoying to deal with. Additionally, when you're creating a gateway, one thing that you have to think about as you're running an additional application and doing extra network traffic is the power usage trade-off, in that the more it will definitely have an impact on the battery life, but our current reasoning with this in these kinds of systems is that if you have a wearable or an embedded device, you want to your first order is to actually conserve the battery life of that device, because oftentimes those aren't charged every day. They're charged on a kind of longer period, and you like it to go as long as possible. So some of the battery hit is offloaded onto the mobile device, which most people charge every day, and so long as it gets through the day, it's probably more acceptable than having to recharge your wearable or an environmental sensor. Next, the server that we built to support all this, its main functions are to store the data from the commands and devices as it's generated, to aggregate it, and to make it available to applications that want to use historical data. An additional feature that we thought about and added was that sometimes you want an application to run beyond just the lifespan of one client web browser, because if someone's running an application in a web browser, they might close their laptop, they might navigate away, and then all of a sudden the application starts running, which is all right in some situations, but for others you want it actually to be more persistent. So we provide an interface that allows you to send a command and actually open up a web application on our server that will have access to the same devices that a fabryq application would have anyways, and run in the background and communicate with the client or user at the appropriate times. And other than that, the server also is essential for keeping track of authentication and whose devices are which and when they've last communicated, and other kind of metadata that's useful from a debugging standpoint. Yes.
Originally you talked about you want to have this centralized piece of code where I can just read and write the devices and display this to a web app or to a web browser. But now you have something that is running in the background.
Yes.
So I open up my web browser. What's the state reconciliation? In the sense that like there's this thing running now in the cloud that isn't that central single point of control. I know I have two things. I've got my web application plus some autonomous agent. So as you mentioned, part of the challenge is working with all these different distributed parts that are operating at the same time. It seems like you've introduced that back in. So how do you reconcile
Yes.
to that state reconciliation?
No, that's a good question. So basically, how do you deal with the fact that you have a client application and a server application, there may be different state, and how can you synchronize and communicate efficiently between them? And our take on that is it's something that we would like to focus on more and make more. It's an area we've identified that can be more or easier to use for the user. But at first we sort of said we want something available to the user in that we would rather have a interface that is slightly more complicated but slightly more powerful than just having a super easy to use interface that is somewhat limited in what it can do. But there's definitely room to improve and have kind of smarter state synchronization or communication that's more transparent between the two instances.
What's the interface like now? It's
Sure.
powerful.
Well, no, the current interface now is a client can open a URL on the server, and it's sort of up to the developer to create a client version and a server version. The client can also restart the server version if it wants to, and they can pass messages back and forth. So just call a JavaScript function, and then the other receives an event with a message of whatever kind that the developer wants to specify. But that's definitely something that we are looking to push on in the future. So in the design of our API, the first goal was to make it as easy to connect to a device and get data from it as possible. So the basic structure is you kind of initialize the fabryq application and list out what devices you have, and then as soon as you have the device object, you can do a get or set or notify command as if you were writing an application that connected directly to the device. We also wanted to make it pretty flexible in that you could easily handle data that was coming from these devices in whatever way made most sense for the application. You could either handle it on a per command basis, on a per device basis, or even more abstractly on the handle data for have one handler for all of a set of devices, or even just all of the devices that the application had. And we also wanted, with our agent interface, to allow long-running applications, even if it takes some extra commands and programming to achieve. As for the actual kind of low-level communication with the devices, we have what we call a protocol proxy, where it allows you to use the same exact commands you would use to communicate with a Bluetooth device as if you were locally connected through the Linux stack or iOS stack. So you can say get and set and notify of the GAT table of any kind of device, any kind of Bluetooth device. And then additionally, we surface various events from the devices and system status, sort of like if a device disconnects or stops notifying you, we have a way for the developer to know that that's happened. As well as we also, as I discussed a minute ago, have a command that lets you start a web application on the server or restart it and communicate with it. And that discussion kind of leads into our thinking with that structure is that most applications of connected devices or Internet of Things devices that we've seen so far seem to follow, or at least their features fall into a kind of sporadic interaction or continuous monitoring paradigm, where sporadic is things like you're adjusting your thermostat or your lights. You open up the user interface, you twiddle it some, and then you shut it off. And you send some commands to it, you maybe get some data from it, but then not much really happens in the background. Conversely, continuous applications, you want some sort of program logic to be running in the background all the time, to be monitoring for different events that might happen, and be able to respond in more complex ways. So if you want your security system to be monitoring in the sensors from the cloud all the time, so it can text or notify you if something bad has happened, and it's kind of useless if you only get figured out once you open up your browser again. And we kind of break down the features. Yes?
Sorry, have you had any already thought of any overlap between those two?
Oh yeah, you can certainly have features in one application that overlap, but there don't seem to be. We haven't thought of really a third kind. Like there are sometimes you say for the security system one, you may want to sporadically change some parameters of the sensors or set your home to be on like away mode or home mode, but that logic and that user interface is kind of different than the logic that's running to monitor everything. And so the features that we've implemented for fabryq, we kind of see support either the sporadic interaction or the continuous interaction mode, where being able to pull up the user interface is very handy for a sporadic app on both the gateway, the phone, and the web. Whereas if you have a continuous application, the logic may be running in the cloud, but sometimes you may want to notify the user, and the client or the agent application can actually open up a web view on the gateway to let the user know about system status or even give them options and respond to it. So as I kind of alluded to earlier, the event handling, we kind of borrow an idea from user interface event handling systems where you have a grid of rectangles where that's hierarchically arranged, that events flow from like more specific cases to more general cases, and if they're handled at any point in the tree, then they sort of get cut off and don't propagate further if the developer so chooses. So in that way, it kind of adds flexibility to whether how you handle the new events or errors that occur as you're writing your application. We also, one thing that was just sort of a practical consideration we made in writing at fabryq was that a lot of these Bluetooth variables, the characteristics and services, are identified by these kind of long, unwieldy 4-digit or 16-digit hex strings. And the data that they output is also arranged in hex strings that generally have meaning based on some specification for published characteristics. So we allow, for certain known characteristics, we have kind of pre-built JSON objects that specify a human readable value that you can use interchangeably with the long hex string, as well as a format or custom conversion functions to take the packed hex data from the characteristic and turn it into something more easily useful. As for the agent interface, I'll walk through a short example of kind of how we see it being used. So it would start by the user opens the client application in their web browser through the web or even through the gateway. Then the client can send a start agent command to the server, which will contain a URL and open up that hosted URL as a web application in a browser instance running on the server. Then that application now has access to all the same devices that the original application would and can send commands to them and get data from them. But also the client and agent can talk through messages that they pass between each other, but even if the client goes away, the agent will keep running until the client comes up again and tells it to stop, for instance. And so that's kind of how the system works. As for how we have evaluated it so far, we've done a few evaluations and learned a lot from each one. The first one was sort of a longer term hackathon that we held to try and work on our hardware prototyping device that I'll talk about in a minute. And we learned a lot about how our previous server and app had some bottlenecks in them. Additionally, we held some shorter hack sessions where we took a student who was familiar with JavaScript but not hardware prototyping and said, here's fabryq. In an hour, what can you do with it? What kind of little application can you make? And then we also made it available to a class at Berkeley, and one of the groups chose to use it and integrated it in their prototype, and I'll be discussing that one in a minute too. So these are 4 example applications that fabryq's been integrated in so far, and I'll go through them one by one. One of the first ones we made was a home monitor for my dorm room at home. It uses a couple TI sensor tags that have both a thermometer as well as a magnetometer and a few other things, but I've realized by placing them over the doors and putting a little magnet next to them, I can track the temperature in the room and the door state and make that available in a web application. And one of the things that struck me as I was writing this is that getting the data stream from the sensors was actually really easy. It took only a couple minutes to actually get it all set up and configured. But the hard part actually then became creating like the entire user interface and making sure that the SVG of my dorm room looked right in the web. And I think it was a good sign that the formerly hard part was not actually really the sticking hard part anymore. And another application that we built on top of the base fabryq infrastructure is something we call microfabryq, which we're trying to think about ways to extend JavaScript's ability and the ability of web programmers to also create physical devices and hardware. And so it's a little prototyping board with a commercially available BLE microcontroller on it that we wrote a firmware for that allows you to, it basically exposes its control registers for its peripherals in the GATT table. So we have an API that allows developers to twiddle those bits and read the digital pins or analog values and set them all over the web. And we borrowed some ideas from the Arduino interface. And microfabryq gives you GPIO, ADC, PWM, as well as interrupts. But so far the main limitation that we've seen is since setting the bits is each a separate command, to write a more complex program or configure it in a more complex way, it takes a while. But it's easy to do because you don't really have to worry about actually flashing it. All the firmware just comes as Bluetooth commands, which we think is pretty neat. Another device that was created with fabryq during one of the 1-hour hack sessions was a page served indicator. So a student had a website that she administrated that had a kind of bursty activity. The people would use it a lot certain times, but not so much at other times. And she wanted to know when a burst was happening. So she made an endpoint on her server and a web app in fabryq that would just check that endpoint saying, has the server served a page since I last checked it? And if so, blink the light. And we thought it was a pretty neat example of how fabryq could be, since it's all JavaScript, all in a browser, it can integrate with a lot of web technologies really easily, as well as other JavaScript libraries. The last device that was made using, or that I'll be talking about, that was made using fabryq was for a interactive device design class at Berkeley. A group of students was trying to develop a sensor to help people with ataxia in their feet that prevents them from feeling their feet as they get older, which actually makes it harder for them to walk or balance. So they wanted to provide a electrical feedback so that when a foot pad felt pressure, it would vibrate a little buzzer motor on their hip to let them know that they had put their foot down. So they achieved the communication between the wireless foot sensor and the hip sensor using a Zigbee radio, but they also wanted to make it available, data from the sensor available online, and they designed a little web app to show the status of the system in using fabryq by integrating a BLE radio as well to their prototype and then connecting it to the user's phone. As for limitations of the system currently, the main ones that we see are that since the whole system, there are several hops for commands to get from a client down to a device across the network. The latency, if the network connections is good, but otherwise can be not so great.
Yeah, can you quantify this?
Sure.
It seems like this is great for prototyping. I want to, see if this new user interaction works.
Yes.
At some point, if I wanted to build this application, in a way that used much less power and had better response times, I'd want to probably not do it in a centralized way.
Mm-hmm.
Except it turns out centralized doesn't cost that much. Maybe it's worth it. So what's the overhead? What's the cost towards a more optimized distributed implementation?
Sure. Cost in latency or power or?
Both, yeah.
Okay. So currently there's a couple of areas that, the current state of the system is it does a REST call to get data to the sensor and back from the sensor. Actually two each way. So one from client to server, another from endpoint to the server. So those, since you, I believe, have to build up a HTTP connection each time, can actually add some latency. So when things go good, it's under a second, maybe 500 milliseconds or so. This could be improved by actually creating a socket connection between the two, and then it would be a good bit faster. So that's kind of the latency picture. So it currently is fine for things where that's an acceptable degree of latency, and less fine where that's not. Notably, sort of, say, like game controllers or things where you need, like, the user perceives the feedback loop. But great for things like pulling sensor data. Power cost in BLE is largely determined by how often you're polling the device and how much you communicate there. But probably the larger power cost in the whole system is the actual phone phoning the server saying, hey, are there any new commands, anything I need to know about? Here are the results of the previous commands. And that, based on the duration of that sort of poll loop, that's, I think, a pretty critical battery consumption factor. And I think those are the main considerations of the system. So another kind of set of applications that we didn't really concentrate on were, there are some Bluetooth Low Energy applications that you can conceive of where you'd have devices coming and going or meeting new devices rapidly and also sometimes losing them. Something like, say, I think FireChat is an example, a kind of peer-to-peer communication system. We don't really support that and are thinking more about applications that are more rigid in their structure, saying, I'm going to start with these sensors, and these are the sensors that the user will use for this application. And then we also hit, as I touched on earlier, a few issues with iOS in terms of what it allows you to do in the background, as well as identifying devices. Both of those would be solved pretty quickly if we made actually an Android application. And that's a fair bit of engineering that we're considering doing in the future. Which ties into what we plan to do next with this project. More gateway support is great. Linux and Android are nice examples of other platforms that we could support with to turn them into gateways as well. It would also be nice, as I also mentioned just a minute ago, to have persistent connections rather than doing a bunch of REST calls, and that could help get the latency down for a command round trip. We also are trying to think about extending what you can write JavaScript for down to the device as well, looking at JavaScript compatible microcontrollers, so you could design an interface that would run similar code on all of them, which could be very interesting, as well as longer term deployments to kind of push on the reliability of the system as well. And that was fabryq. Thank you very much for listening. Any questions? I think you have one.
I just wonder if you can expand on the last one, longer term studies, an example.
Well, we'd like to actually see it. Most of the applications are sort of prototypes. Is this a neat application? How does this work? For a period of, say, hours. But we would want to see it used for deployments for like days or weeks. And if/when it crashes, fix that, and so to make the whole system more robust is what I was going for. Yes?
So one of the things that you do encounter in real life is servers fail for lots of reasons, not just because of software failures. Do you put any energy into thinking about the high availability aspects of the server side?
No, we haven't really considered that as much, or even so much like scaling between like multiple servers. And I can think of some sort of like straw man ways of doing it, saying, okay, these users live on this server, those users live on that server. But we haven't gone that direction so much. Yes?
Well, mobile internet connections are fairly unstable depending where you are.
Yes.
And do you have a mechanism in there for recovering the state, or between mobile app and server app, that does the client get notified that there is no connectivity available? And if you have queued up a bunch of commands that you send down to the device, what's happened to them? Do you discard them, or
Yeah.
what do you do in this area?
No, yes, that's a good question. Sort of, what steps have we taken for dealing with network unreliability between, across the whole stack? And we've done some work on that, but haven't made it, or haven't done as much as we'd like probably. The things that are definitely implemented are the client gets notified if either a gateway device drops out or a client device stops sending data. So you can receive an event about that and handle that appropriately. Additionally, commands that get sent to the server are queued there until they can be executed. And until it gets down to the gateway, gets executed and comes back, it will still be queued to be executed later. Things get a little bit more corner casey and difficult, saying, okay, the phone has executed these commands, but in the second before that the results make it back to the server, the network goes out. We don't handle that particular corner case yet, but that's kind of the state of what we have so far. Yes?
So it seems like this is great for prototyping, but the idea that I can suddenly start spawning web browser applications on servers to proxy as my web browser.
Yes.
I'm wondering just about how hard it's going to be to transfer, to sort of transition from this particular prototyping architecture into working systems, for example, that includes issues such as security.
More security.
Of devices, right? Like, this is good for prototyping the user interaction.
Yes.
Right? But from then how I would transition that to a working robust system, I'm wondering if some thoughts of other ways or mechanisms you could add to make that simpler. Like, it could be that, hey, I don't want a server. Instead, the server should do is act like a web browser, just act as a client, and then push everything to the client, take the server out of the equation.
Yes. No, that's a very good question. Sort of like, what are the considerations from scaling up from prototyping interaction to actually making a more robust and secure system? So I guess I kind of will go through things that we have done and things that we'd like to do. Things we have done are we do enforce basic authentication. So users own devices and other users can't access the information from them. And a given application belongs to a certain user and it uses devices that they own. And so the server enforces some degree of permissions. And we do have like SSL on the connections between the client and server and endpoint. But then as to things that we'd like to do more, certainly for the spawning browsers one is a good example of, we did it because you can prototype a fairly powerful application fairly simply. And being in a web browser offers you some degree of sandboxing. And it's something we have thought about. Well, you could move it to a different server that's completely different than the actual server that contains much. So even if it's somehow compromised, it's not really as big of a deal. And as for kind of making the whole system more robust, we haven't put as much effort into the sort of system aspects there. Probably a long-term vision is this project, the goal of it was to prototype how the user would write code for these systems, and we would ultimately be writing sort of a user interface or API on top of a more robust kind of systems or more robust underlying computing system.
Great. Well,
Thank you.